Hello, welcome back to Chapter 13, Section 1, where we're introducing right angle trigonometry, the study of the ratios of the lengths of the sides for right angles. In the first video, we introduced what we nicknamed SOHCAHTOA. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. We're going to bring back that idea in a second, but we're also going to include something that maybe you did in geometry. I know it's in the geometry textbook, so hopefully you did it. We're going to talk about two special right triangles. And when we say there's an infinite number of them, but we're talking about all of the triangles that are similar to one special triangle and all the triangles that are similar to another special triangle. Okay, so the two triangles we're going to talk about are what we call the 45-45-90 or 45-45 right, and we're also going to talk about the 30-60. That's supposed to be a 6. 30-60-90. Now these actually have lots of applications in lots of places. Just real quick, I know this is a video, I don't want to get too deep in nostalgia with this one, but one of my favorite classes that I took when I was in high school was drafting. And we don't do it anymore because no one draws things by hand. It's all computer-aided design. If you're taking any of those 3D modeling classes with Miss Corbett or Mr. Manning, or if you're watching this video in the future and there's some other teacher doing it, that's just great. But my favorite class, because I took it at the same time when I was doing geometry, so both of them are together, and I don't know if I can get this whole on the screen, we use these things. Okay, you can still buy these. I've got them in my classroom. You can still buy these at like art stores and other places. And what we would do, I'm trying to maneuver this so you can see it. What we would do is we would have these plastic triangles, and we would set up our paper on a board, and we use what's called the T-square. I know I've got my T-square here, but I couldn't actually find it. And I've got a couple of them in the classroom, and I'll show them to you. They were left over by a previous teacher, actually. But anyway, you can draw like 3D views of objects using these triangles. This is the other one that we use. I'll try to fit that in. These are big versions of them. I got smaller ones in my classroom. But this is a 45-45-90, and this is a 30-60-90. So like this angle right here is 30 degrees. This angle right here is 60 degrees. And this is my right angle. And this, we use this, or on the other one, we use this to make perpendicular lines to the T-square. This is 45, and this one's also 45. Now, the angle measurements that start with 30, 60, 90, 120, 150, 180, 210, 240, you can keep going all the way to 360. These are going to be very important angle measurements as we study more about trigonometry. Also, we're going to throw in the 45s. So 45, 90, 135, 180, 225, etc. You're going to be seeing these show up in a couple sections from now as we go around what we call the unit circle. What's special about these triangles? Well, this is too big for me to draw it on the paper, okay? So I'm gonna just sketch this a little bit. If I start with a 45-45-90, I want you to notice one thing about this. So if this is 45 degrees, and this is 45 degrees, this is a special type of triangle. Outside of just 45-45-90, it's special because it is isosceles. And I'm not going to do this in this video, but if I was teaching geometry, we would talk about doing a proof of showing that if the two complementary angles of a triangle, of a right triangle, are congruent, then the two legs are congruent. This leg is congruent to that leg. That's what makes it isosceles. So same angle, same leg. Actually, I think the way we usually start is we say we start with an isosceles triangle, then we prove that the two angles are congruent, and then also there's the converse of that. So if the two angles are congruent, then we can prove this isosceles. I know that these are both 45 because that's the triangle that I'm drawing, and I know that this last angle is going to be 90 because 45 plus 90 equals the 180 we want. So check this out. What about sine of 45? All right, so let's just pick some numbers here and see what happens, because remember from the previous video, we know that as long as I have a 45, 45, 90, if I drew this, I know this one's much bigger. If I drew this as a 45, 45, 90, I know it's just a scaled version of every other 45, 45, 90. They're all similar, so the ratios should be the same. So I'm just gonna pick a number. All right, I'll pick 5. So for example, if this is 5, that means that this side also has to be 5 because it's isosceles. So far, so good. But what's this side? Turns out that I can use the Pythagorean theorem to figure this out. I know that 5 squared plus 5 squared, that's 25 plus 25, which is going to be 50. So this right here is going to be the square root of 50. But I need to see if I can simplify that radical, that square root, and that is something that we have actually done before. We did it in chapter 1. So I know that I can simplify by factoring out the 25. So the square root of 25 times the square root of 2. What's the square root of 25? It's 5. So this is going to be 5 times the square root of 2. And one thing about it is, notice that I've got a 5 here, a 5 here, and there's a 5 multiplied by the square root of 2. If I'd pick any other number here, I would have got the same thing. This was like, what if I'd said just 1? This would have been 1. This also would have been 1. And this would have been 1 times the square root of 2, or just the square root of 2. So the ratio actually, in simplified form, is going to be 1, 1, I'll use colons, square root of 2. In this one, because I picked 5, it's 1 times 5, 1 times 5, and square root of 2 times 5. So I can simplify it by using this easier ratio instead of the one with the 5s. Okay, that's cool. What about sine? Well, sine is going to be, and by the way, both of these are the same, so it doesn't really matter. I'm going to use this one. Sine is going to be opposite over hypotenuse. That would be 5 divided by 5, and that's where the 5s reduce. So in reduced form, I just get 1 divided by the square root of 2. I can't leave that, but while I'm talking about it, cosine of 45 is also 1 divided by the square root of 2. Okay, now I said I can't leave that. The reason why is because I have to rationalize the denominator. So this actually becomes the square root of 2 over 2. And same thing, square root of 2 over 2. So make sure that you rationalize your denominators. What about tangent? Tangent of 45 degrees, if I use my original triangle, it's going to be 5 divided by 5, which just equals 1. If I have 1 divided by 1, if I take out the scale factor, again, that just becomes 1. Okay, so these are the ratios that I know based upon the 45, 45, 90. Now let's talk about the 30, 60, 90. 30, 60, 90, my big version looks like this, all right? So I'm going to try to draw it this way. So again, here's my 90 degrees. This is my 60 degrees. And I'm going to put this in like here, 30 degrees right here. All right, so how do I do this? What I do? I start off by just, over here I just said, well, pick one of the legs to be 5, and it turns out that that could have been a scale factor. So if I pick one of the legs of the hypotenuse to be a number, maybe I'd be able to do the same thing. But I won't be able to use the Pythagorean theorem yet, keyword yet, because since that's 60 degrees and that's 30 degrees, these two legs are not the same. Last time it was nice because they were the same. So as soon as I had one, I had the other one. In order to use the Pythagorean theorem, I need two of the sides, whether both legs or one of the legs in the hypotenuse. So this is the genius thing about this. This is what's really, really cool about this. What I'm going to do is I'm going to take my triangle right here, and I know you can't fit it all on the screen. I'm going to take my triangle and I'm going to flip it over on this side. Why? Well, check it out. So I'm going to do it with a dash line. So now I want you to look at this triangle right here. I know I've got this part, but I flipped it over here. I want you to look at this triangle I have here. This angle just flipped over here, so this is 60. And this angle flipped over here, so that meant that the other angle is 30. And this kind of makes sense because in my new big triangle, this is 60 degrees, this is 60 degrees, 30 plus 30 is 60, and all of them add up to 180. So guess what? The big triangle is equilateral. All three angles are 60 degrees, and again, that means that all three angles are going, all three sides are going to be congruent, making an equilateral. So how's that going to help us? Well, let's say if I actually picked this side here, this would be 3. And when I flipped it over, now that's 3, and 3 plus 3 equals 6. And because this triangle here is equilateral, from here to here is 6. That means from here to here is 6. All I need to do now is figure out this side, and I can use the Pythagorean theorem again. So I've got 3 squared plus, and I'm going to use x, equals 6 squared. Oops, equals. I didn't write that. So I didn't give myself no space there. I'm sorry. So I'm going to get 9 plus x squared equals 36. And 36 subtract 9 is going to be 27. Okay? So x to the second power is going to be 27. And inside here, this side, is the square root of 27. But check this out. 27 can be, the square root of 27 can be simplified. This can be simplified, square root of 9 times the square root of 3, and the square root of 9 is 3. So this is 3 times the square root of 3. So just like I was able to simplify this triangle over here, I picked 5 to start with to explore it, and I found out that I can reduce it to a ratio of 1, 1, square root of 2. This is 3 times 1, this is 3 times 2, and this is 3 times the square root of 3. So my ratio is going to be, 1 to the square root of 3 to 2. And that's short leg, long leg, hypotenuse. Short leg, long leg, hypotenuse. So the sine of 30 degrees. The sine of 30 degrees, and my 30 degrees is right here, is opposite over hypotenuse. In my original triangle here, the fraction is 3 over 6. 3 over 6 is going to reduce to 1 over 2. And that's short leg over hypotenuse. The cosine of 30 degrees is going to be, and here's my 30, the adjacent side over hypotenuse. Adjacent is 3 times the square root of 3. Hypotenuse is 6. That's going to simplify to square root of 3 over 2. It's the long leg over the hypotenuse for the 30 degrees. It's not always long leg, okay? And the tangent of 30 degrees, here's my 30 again, opposite over adjacent, so 3 divided by 3 over square root of 3. The 3's are going to reduce, and I get 1 over the square root of 3, And if I rationalize my denominator, I'm going to get square root of 3 over 3. Now that's the 30. Let's talk about the other angle, the 60. The sine of 60 is going to be, here's my 60 degrees, opposite over hypotenuse, 3 times the square root of 3 over 6. That's the square root of 3 divided by 2. Pause for a second and notice something about that. The cosine of 60 degrees, here's 60 degrees, cosine is adjacent over hypotenuse, that's 3 over 6, which reduces to 1/2. Notice something about that too. And the tangent of 60 degrees is going to be opposite over adjacent, square root of 3 over 3 divided by 3, which just leaves me square root of 3. Now the thing I was hoping you would notice is this. The cosine of 30 degrees is the same as the sine of its complement. So these are both square root of 3 over 2. And the sine of 30 degrees is the cosine of 60. Cosine actually means the complementary sign. It's the sign of the complement. So that's where those things come in together. Okay, so these are some really important numbers that you should know, and I'm going to summarize them right here. And of course, I'll take a picture, and this is in your book. So I started off by showing any 45, 45, 90. I just chose 5 as an example, but I knew that that was a scale factor that can simplify my ratio. So, I'm sorry, I'm doing this one. So then this is my most simplified, most reduced version. If the legs are both 1, then the hypotenuse is square root of 2. And of course, it doesn't matter how long the leg is. If the leg was 95, this would be 95, this would be 95, and this would be 95 times square root of 2. But when I find my sine, cosine, and tangent, that scale factor 95 is going to simplify. It's going to reduce. It's going to factor out. For the 30, 60, 90, we get the ratios by making an equilateral triangle and then figuring out that the short leg is always half of the long leg. So excuse me, I said that wrong. Rewind. The short leg is always half of the hypotenuse. Okay, apologize for that. And using the Pythagorean theorem, we find out that the other leg is going to be square root of 3. And again, I can scale that up to whatever size I want. So if this is 7, this is 2 times 7, which is 14, and this would be 7 times the square root of 3. And I'd leave it 7 times the square root of 3. We've worked with radicals before. And we've got sine 30 and sine 30 and sine 60, cosine 30, cosine 60. These ratios are the same as what we figured out over here. So, I know this is really important stuff. That's why this video is going a little bit longer. So, how do I use a trigonometric function to find a missing side length? So, it looks like I have a 30, 60, 90 triangle here. All right? If this is a right angle and that's 60 degrees, that means this is 30. Easy peasy. It's all right. I want to find out what x is. So, the first thing I need to do is figure out, relative to 60 degrees, which trig function am I using? Relative to 60 degrees, I've got 2 legs here. This is the opposite leg, and this is the adjacent leg. It's not asking me to find the adjacent leg. That'd be the next step. But I'm actually trying to figure out what the opposite is. What did they give me? They gave me the hypotenuse. So which trig function uses opposite and hypotenuse? That's sine. So I want the sine of 60 degrees. And the sine of 60 degrees equals, in this triangle, opposite over hypotenuse, x over 100. Now what I need is to figure out what the sine of 60 degrees is. If I use my scientific calculator, it's going to give me a decimal. And actually that decimal is an estimation. But all I really need to do is use my fraction. So I'm looking for sine 60 degrees. It's right here. It's a square root of 3 over 2 which actually is what I had right here, square root of 3 over 2. So this becomes the square root of 3 over 2 equals x divided by 100. And you can cross multiply. I know that's kind of like a middle school thing. The opposite of dividing by 100 is to multiply by 100. So I'm going to multiply both sides by 100. And I'm going to put the x over on the left now. 100 times the square root of 3 divided by 2. And I can simplify 100 divided by 2 is 50. So x is going to be 50 times the square root of 3. Let's do a similar problem with a 45, 90. Which trig function am I going to use? Well, again, I'm using opposite over hypotenuse. So now I'm going to use the sine of 45. And in this triangle, that's x over 20. So let me check out sine 45. Sine of 45 is 1 over square root of 2, but we don't write it that way. We write square root of 2 over 2. I'll let you in on a secret. Sometimes we actually do use this, but we don't leave it as our answer. Sometimes we do it if we know we're going to do more to it. All right? But I'm going to use square root of 2 over 2. And that's going to equal x over 20. I'll multiply both sides by 20. And I get 20 times the square root of 2 over 2. And I'll turn it around now. 20 divided by 2 equals 10. So I get x equals 10 times the square root of 2. And you can just leave it like that, simplified radical form. All right, I'll be doing more examples like that when we get to the guided practice problems.